Hi there. In this section, section 7.8, we're going to talk about a new operation called convolution. And it's super weird, and everyone thinks it's super weird, but it ends up being really useful in a lot of different applications. And the one place where you might have heard of it before is if you have sort of read anything about deep learning and artificial intelligence and machine learning and all that fun stuff. There is a concept called, or there's a kind of a method for, doing image classification and that sort of thing, which is called convolutional neural networks. And so if you've heard of that term, the convolution is exactly the same convolution that we're going to learn now. There's a lot of different ways that you can kind of motivate it, and none of them really matter for the purposes of this class. But the way that I think of it is kind of like an averaging function. So the motivation for why we're doing it is to consider that we have some sort of initial value problem that looks like this. Y double prime plus y equals some function of t, and then we've got easy initial conditions, y prime of 0 equals 0. And so the way that we solve this with a Laplace transform is to let, not big G, let big Y be the Laplace transform of little y, and then big G can be the Laplace transform of little g. And then if we take the Laplace of both sides, and we end up with this s squared y plus y equals g. And then if we solve for big Y, we get this 1 over s squared plus 1 times big G of s. So we have formulas. We have for the inverse Laplace transform of, let's say, f plus g being the inverse Laplace of f plus the inverse Laplace of g. But what about when you have a product? So that's what we've got up here. We've got something times something else. So what if we have that? Do we have a formula for breaking apart the inverse Laplace transform? Well, that's what we're going to figure out in this video. So let's get our definition up here first. So let's let f of t and g of t be piecewise continuous functions. We need them to be piecewise continuous so that we can take an integral. We'll say on 0 to infinity. The convolution of f and g is defined by, so the way we write it is f star g of t. And this is going to be defined by the integral from 0 to t of f of t minus v g of v dv. So I'll point out that in the book, the way that this is actually notated, instead of a v, it's a nu, like the lowercase Greek letter nu in U, but I'm not gonna try and confuse you like that, mostly because my news look too much like V's, and that'll, I think, just be too much. So we're gonna use V as our integrating variable. So this is where we're integrating, and we've got a V there. And then we have the T is the limit. So that's what makes this sort of so weird, is that we have one variable that's in the limit and changing, and that's also the same variable over here. And so, but then you're integrating all the way up to T, up to that point, you're sort of shifting T around by V and then multiplying by G at that function. So it's a little bit like an average, because you're adding it up and weighting it. So you're weighting G by how much F is going to shift over it. So now there are some nice properties of convolution. So I'm not going to prove any of these because I don't want to. Properties of convolution. Let's see. We get that F star G equals G star F. So you can switch F and G around and it's going to be the same thing. That's pretty nice. So that's commutativity, right? And then we have associativity too. So F star of G plus H equals F star G plus F star H. And that you can probably see fall out immediately from the definition of the integration. So I guess this is distributive, right? Not associative, distributive. And this is commutative property, commutative. And then our third one is F star G star H equals F star G star H. So this is associative. And then the last one here, F star 0 equals the 0 function, which again is pretty obvious. If you change G to 0, then that would kill the whole thing. And so this is, I don't know a name for that. So convolution has some of the same properties as multiplication. Not all the same properties, but in some respects it sort of operates similarly to multiplication. Okay, so now we've got a theorem where we'll see that convolution actually operates similarly to multiplication, in the sense that in one universe, convolution in one universe is multiplication in the other. So let's state our theorem, the convolution theorem. Let F and G be piecewise continuous on 0 to infinity and of exponential order. That's so that we know we can take the Laplace transform. So we'll let big F of S be the Laplace transform of little f. And similarly for G, big G is the Laplace transform of little g. Then the Laplace transform of the convolution equals the product of the Laplace transforms or another way to write this, the the inverse Laplace transform of the product, f times g, is equal to the convolution. So this exactly answers the question that we asked before. How do we take the inverse Laplace transform of a product? And it's the answer is that it's the convolution of the inverses. So another way that we could write this would be the inverse Laplace of f convolved with the inverse Laplace. Oh, sorry. The inverse Laplace of big F is equal, blah, blah, blah. Whatever I'm writing is right. So the inverse Laplace of the product is equal to the convolution of the inverse Laplaces. Okay. Okay, let's prove this. Let's try to make that small. Hold on. Okay, I'm going to keep that statement written over in the corner real small so that I can refer to it. So proof. Let's start with the Laplace transform of f convolved with g. Okay, so we're going to just use the definition. So we've got, for the Laplace transform, we have the integral from 0 to infinity, e to the negative st. And now the convolution is another integral. So that's the integral from 0 to t, f of t minus v, g of v, dv, close bracket, and then dt on the first integral. Now, it's actually going to be useful for us to make sure that both of the integrals have the same limits. So we're going to rewrite the inside one so that it goes from 0 to infinity. So let's do 0 to infinity, e to the negative st again. And I can make this one be 0 to infinity if I introduce a unit step function and just like sort of pretend that I killed off, or just make sure that I kill off everything that wasn't getting integrated by this. So I can just stick in my u of t minus v and then keep everything else the same. G of v, dv, and then dt. So now let's think through about why that makes sense some more. So if v is between 0 and t, then u of t minus v is going to be, well, let's say it this way. Then t minus v, t is bigger than v, so this thing is going to be positive. And that means that u of t minus v is equal to 1. So in this case, then the integrand equals f of t minus v times g of v. Okay, and then so it's the same thing as up here. Whereas if t is less than v, then t minus v is negative, and that means that u of t minus v equals 0, and the integrand equals 0. So that's why that means that this integral here is exactly the same as this one. Okay, those red marks are not terribly clear on their own, but hopefully my words have explained it well enough. Okay? Okay, so now I can kind of pull the integrals together. So I can bring the e to the negative st inside that second integral. e to the negative st u f g g of v dv dt. And because f and g are of exponential order, that means that these integrals are defined. This whole integrand it's not going to kind of blow up if we integrate over 0 to infinity. And that allows us to switch the order of integration. Okay, so let's do that now. Well, okay, ta-da. And now that our inner integral is a dt, we can pull out this g that doesn't have anything to do with t. So now we're going to be 0 to infinity g of v, integral from 0 to infinity, let's put a bracket here, e to the negative st u okay, now this is a dt, close bracket, dv. Now let's move on up here. This integral in brackets is the Laplace transform. You see it's the Laplace transform, right? E to the negative st times the u times f function. So this is the Laplace transform of f of t minus v times u of t minus v. And we saw in section 7.6 that this is equal to e to the negative vs times the Laplace transform of f of t of s. And this is from section 7.6, page 386. And so we can keep our equality going. So this is going to equal the integral from 0 to infinity g of v times e to the negative vs times that Laplace transform of f is just big F of s dv. We can pull the big F out, and we've got the integral of g of v times e to the negative vs dv, but this guy here is exactly big G, the Laplace transform of g, so this equals big F times big G. And so that is exactly the proof. We started off with the Laplace transform of f times g, and it equals this guy, the product of the Laplace transform, and that's the end of the proof. So the last thing I'll say for this video is suggest that you do some exercises. I'm sure there'll be some in the homework. So the exercise is going to be using this theorem to solve ODEs. And I'll probably end up doing an example of this in lecture as well. So we'll see that then. Or you can read the book. So e.g. Example 1 on page 399 and 400. All right, that's it for the video.